Today we're going to talk about Chapter 1, Controlled Experiments. So first, how can we design an experiment? So for example 1, the first polio epidemic hit the United States in the early 1900s. By the mid-1900s, hundreds of thousands of people, mostly children, had died from the disease and many more were left paralyzed. Jonas Salk produced one of several polio vaccines, and they were ready to test it by 1954. So the main question is, how does one determine whether or not the vaccine is effective? So one thing you might try is give the drug to everyone and see if the rates of infection decrease. But if you remember that polio is an epidemic disease, which means the rates fluctuate dramatically from year to year, what would be wrong with the above approach? Well, you might just happen to give the vaccine to people, and then the next year the rates just might be going down already. So the rates might go down just coincidentally. Okay. So nothing to do with the vaccine. Or for an alternative, you could deliberately leave some of the individuals unvaccinated and record the disease incidence. Or record the rates of how many people, of the unvaccinated people, get polio and how many people with the vaccine get polio. And that's the method of comparison. So for our method of comparison, researchers compare the response of a treatment group and a control group. And when the treatment and control groups are similar, apart from your treatment, then a difference in response is likely the effect of the treatment. One of the ways that we like to compare is with a controlled experiment. In a controlled experiment, the investigators, experimenters, or researchers determine who receives the drug and who does not. So for example 2, again, we're ready to test the polio vaccine on people. And so they went and they vaccinated grade 2 children whose parents consented. Now, the people that were vaccinated, we call that the treatment group. And then they use grades 1 and 3 for controls. Controls meaning the people that were not vaccinated. So then the controls are the people that don't get the treatment. Now, this was a controlled experiment because the investigators were the ones deciding who got the treatment and who didn't. But it was not a well-designed experiment. Okay, this was a bad experiment. One of the reasons why is that your control and treatment groups should look alike in as many ways as possible, except for one will get the treatment and one does not. So again, you want your two groups to be as identical as possible, except for the fact that one gets the treatment and one does not. So how did the control and treatment groups differ in this experiment? Again, keeping in mind that this was a bad experiment. So how were the groups different? Well, for one reason, age. So vaccines only went to second graders, and so maybe there was an age difference here that made a difference in the polio. Now it's probably unlikely that it affected first and third grades the same way and second a different way, but it is possible. The other difference is that only the kids whose parents consented got the vaccine. Now, this might not seem like a big deal to you, but we found that people that are willing to participate in experiments are often different, or are in a different demographic than people that are willing to give consent. And so maybe these families were richer, or poor, or better educated, or worse educated, but there could have been a difference here. And so maybe those differences were actually causing the differences in whether or not they got polio and not the actual vaccine. So the difference was all the kids whose parents consented, or only kids whose parents consented, got the vaccine. But all kids in the 1st and 3rd grade didn't get the vaccine and were included in the study. So again, maybe the difference here was based on what demographic the children were in. So now, confounding factors. If two groups differ with respect to something other than the actual treatment, in this case the vaccine, we say that there is a confounding factor. So if your treatment group is, say, younger than your control group, then age would be a confounding factor. Or if your treatment group is healthier than the control group before the study actually starts, then initial health would be a confounding factor. Or if your treatment group has a higher socioeconomic status than the control group, then your socioeconomic status would be a confounding factor. So in our last example, age and whether or not you consent to a study would both be confounding factors. So we've talked about one bad study. Now let's talk about how to design effective studies. One of the most important factors is randomization, because if we can randomly assign subjects to the treatment and control groups, then we ensure that we have a better chance that the two groups are similar. When your groups are randomized, that means we're selecting them with some means of a chance mechanism. So for example, coin tossing or computer generating random numbers. The randomization reduces human bias because people don't get to decide who gets the treatment. So for example, if physicians get to choose who will get a surgery, they may subconsciously put the healthier patients into the surgery group because they're healthy enough to undergo surgery. And then that would bias their study, because if only healthy people are getting the surgery in their study, it's going to make it seem like the surgery is more effective. But in a randomized study, all the participants to start with must be considered healthy enough to undergo the surgery, and then people are just randomly assigned into surgery or not surgery groups. The next factor is blindness. If subjects know which group they're in, they might react to the idea of the treatment instead of reacting to the treatment itself. So it's good to have a blind experiment where subjects don't know which group they're in. Also, if investigators know which group the subjects are in, they might treat the groups differently, or they might treat the person differently. So it's good to have a double-blind experiment where neither the subjects or the people who interact with them know which group they're in. And finally, a placebo. A placebo is a neutral treatment, such as a sugar pill or saline injection, where it doesn't do anything. And this is used to avoid possible psychological effects that can arise when a subject knows whether or not he has received the treatment. Because oftentimes just thinking that you're getting help will make you feel better. Placebos help a study be blind. That way, obviously you know you're not getting the treatment if you don't get any pills. So if we give everyone a pill, whether it's a placebo or their treatment, then it helps the study be blind. And we found, for some reason, that big, colorful placebos work best. As far as people believing that they're getting help. So for our next example, a randomized controlled double experiment. This is an example of our randomized controlled double experiment. So after they did the first polio trial, they said, oh, we didn't design this very well. So they went back and did another trial. So experimenters asked parents of children in grades 1, 2, and 3 if they would consent to the polio vaccine. Then the children of the consenting parents were randomly assigned to the control, which means no vaccine, and the treatment groups. The untreated children received a placebo, which was just a salt and water injection. And the experiment was double-blind because neither the doctors examining the children nor the children themselves knew who belonged to which group. For our next example, Let's go through some of the methods that you could use to randomly assign people to treatment and control groups. So we'll go through each example and see if this would be a good way to randomly assign people. So the first one, have the researcher assign subjects to groups without knowing anything about them but their names. The problem with this is it might sound good, but names vary according to gender, ethnicity, age, and so the researcher might have some unconscious bias. So you can be biased about gender. It's usually fairly easy to tell if it's a boy or girl by their name. You could be biased by their ethnicity and by their age, and maybe something else that you can think about. The next one, draw names from a hat. That would actually be okay. Shouldn't get too much bias if we just draw names from a hat. And the next, roll a die for each subject. Even numbers go to the control group, and odd numbers go to the treatment group. This would also be an okay method because it has nothing to do with the actual person, so we shouldn't be biased in any way. Now, someone has pointed out before that we won't necessarily get the same number of people in each group. Although it should be roughly about half and half. So we won't necessarily get the same number of people in each group. But that's okay. That's not actually important in statistics to have the same number of people in each group. You can have different numbers of people in the two different groups. And example 5. In an experiment designed to test the effectiveness of asthma medications, each subject is assigned to drug A, meaning get your drug by an inhaler, or drug B, which you get it by a shot. A physician later examines each patient to determine whether the symptoms have improved. The physician is unaware of the treatment received by each patient. The question is this experiment double-blind? Why or why not? No, this would not be double-blind because the patient knows which treatment they are in. Because it's pretty easy to tell if you're getting a shot or an inhaler. So the patient knows. So technically here, the doctor is blind. The doctor didn't know what treatment they got, but the patient isn't. Now let's talk about historical versus contemporary controls. So historical controls are patients that were treated the old way in the past. And a randomized experiment may be hard to do, so researchers may use less efficient designs, such as historical versus contemporary controls. So you may try a new treatment on patients and then compare that to your historical data or your historical controls of people that were treated with the old way. Historical controls may differ from the treatment group in more ways than just the treatment, though. So maybe if we're comparing our new treatment to people that got a treatment, say, 20 years ago, maybe our diets have changed since then, or exercise patterns, or other things like that. So the best experiments have contemporary or current controls. There are some limitations of controlled experiments. So as we said before, when our treatment and control groups are similar apart from the treatment, then a difference in responses is likely the effect of the treatment. And so a well-designed controlled experiment can show that a treatment causes a response. Unfortunately, it's not always possible to conduct a controlled experiment. So when might it be impossible to conduct our controlled experiment? There are various reasons that we could have a problem with this. So for one, a common example is that you can't do controlled experiments with smoking. Smoking cigarettes, because you can't force people to smoke. Okay. Since we know that smoking is dangerous, it's unethical to force people to be in the treatment group of where they would be smoking. Okay, other things, your weather in plant studies can't be controlled. Or you might have problems with large predators are dangerous, so you can't necessarily force people to work with large predators. Really the biggest one is that you can't control people's lives too much. So there's things that you can't make people do. You're going to have a hard time forcing people to smoke or drink. You're going to have a hard time convincing people that they want to participate on, say, a very strict diet where they can only eat what you say they can eat. Okay? Or you might have a hard time convincing people to maybe exercise the exact amount you want. And we can't do things like force people to change their major to something we want. So again, you can't control people's lives too much, and so it makes it difficult to conduct controlled experiments sometimes, especially with people. So, in summary, if we want to evaluate a new treatment or therapy, we need to use the method of comparison. This is the best way to do it. We want to compare the subjects who received the new treatment to those who received no treatment or a standard treatment, which would be the control group. If the treatment and control groups differ with respect to factors other than the treatment, the confounding factors that we talked about, then the effects of these factors are confounded with the effects of the treatment. To eliminate confounding factors and bias, assign the subjects to the treatment and control groups by some random mechanism. To eliminate possible biases, we prefer that the experimental subjects don't know who received the treatment and who received the control. Such an experiment is to be said to be blind. And to make an experiment blind, the subjects in the control group are often given a placebo, which resembles the treatment in every way, but is inert. It's also desirable that the people evaluating the experimental subjects don't know who received the treatment and who received the control. Such an experiment is said to be double-blind.